Soalan mana yang paling senang? Yang lain semua senang kan? Betul. Two for you. Okay, two was on. Okay, pattern oxide, right? Two pattern oxide. Kita baru discuss je. I think 1 or 2 sessions back. Pattern oxide. How do we do patterning of silicon dioxide? It's very straightforward. Even though it's an open book test. So yeah. So how's question one? Question one is quite okay, right? So we've learned about gathering, and the request from the question is quite straightforward. I think a little bit difficult one is question 3, because you need to understand something to be able to propose your CD value, and you have to justify as well. So that's probably the hardest part of the test. But being an open book test, so I think it's quite okay if you combine slightly easy and slightly difficult, because you can search after all. So then it depends on how do you use your understanding to stretch to get to the question. All right. So now let me share the etching lecture notes. Let's continue. Before we start, I'm still waiting for Osram to confirm on the engineer's name for the 7th and 8th December sessions, class by Osram. They've agreed though, but I'm still waiting for the name. And you're gonna have 2 more sessions lepas tu. Sekejap We're gonna have one on 18. We're gonna have a sharing session from Physics alumni as well, from Infineon. And I think before that, just now was 18 for Infineon. And on the 10th of December, Thursday, we're going to have a sharing session as well by your senior as well from Intel. Okay, from Intel, from Infineon, then from Osram. So then you're going to have quite quite a wide perspective for your internship and for your career as well. All right, so let's move on to the lecture notes. So last time we have discussed about introduction to etching. So let's recap a few things before we move on about the etching process. So when you are asked to define etching, how would you define the process? In simple terms, how would you define etching process? You can type there, or you can unmute yourself before we start. How would you define etching process? What are the keywords? Right, yes, removal of material, right? Removal of material. So that's the most important keyword you've got. Removal of material, and it can be done by multiple methods. So it depends on the etch rate and so on and so forth, right? But the essence is removal of material. So how many types of etching do we have? How many categories do you have? Wet etch and dry etch. Okay, yes, good. Wet etch and dry etch, just like oxidation process, wet and dry. Okay, so what is the gist of wet etch? If we say wet etch, then how would you say about wet etch? Apa beza antara wet and dry? right? Wet etch uses wet chemical. How about dry etch? Dry etch uses plasma. Good, right? Then we have also learned about anisotropy, right? So how would you define anisotropy? So what do you understand by anisotropy or versus isotropy? Or anisotropic versus isotropic? Anyone? Yes, good. Unidirectional versus non-directional. Okay, which one is unidirectional? Is that satu direction? Right, good. Anisotropic means one direction or unidirectional, and the other one non-directional or isotropic. So unidirectional etches one direction a lot faster than the other directions, and non-directional or isotropic, it etches all directions with the same etch rate, right? So either it's nanometer per minute, nanometer per second, micron per minute, or micron per second, or even micron per hour, or even nanometer per hour. So it really depends on what sort of etching are you talking about and what sort of material are you handling, right? So those are the G's of our previous discussion on etching process. So let's move on. So we have stopped until this point where you have seen a very deep well with a very high aspect ratio. So aspect ratio is defined as height over width of a particular structure. So in this case, it's about 4:1 or 5:1, right? So you can actually measure the aspect ratio of an etch structure the moment you see your SEM data, especially from cross section. And to be able to see clearly, you need to have a scale bar on a cross-section image. So in this case, there is no scale bar, but judging from the width and from the size is somewhere 4:1 or 5:1. But to be accurate, you have to use the scale bar on the FISM cross-sectional image. So now let's look at characteristics of wet etching process. Usually the wet etching, alat yang kita nak guna untuk etch tu is called etching. Just like the way we talk about oxidation process, the precursor material we use to do the oxidation is called oxidant, and this one is called etching, right? So wet etching ke dry etching ke. So for wet etching process or wet chemical or chemical solution, they are usually highly selective in order to be able to remove certain materials and don't remove certain materials. For example, if you talk about HF etching in silicon dioxide etching in HF solution, so in that case, the selectivity of the HF has to be very high towards silicon dioxide in comparison to silicon, so that eventually silicon dioxide can be removed from silicon and silicon remains as it is. The second one, wet etch is generally isotropic. So that means it etches material in all directions with equal etch rate. However, there are cases when wet etch can also be anisotropic. We'll see later on, right? But generally, it's isotropic in nature. So that means if you talk about etching of silicon dioxide on a silicon wafer, so it's going to etch all directions with equal etch rate. Then only you can remove the silicon dioxide on the wafer successfully. If, for example, if you imagine HF etching silicon dioxide anisotropically, so that means you're gonna be left with some residue of silicon dioxide on the silicon wafer because the etch rate is not uniform in all directions. Typically, wet etch is used for features larger than 3 microns. Well, usually if you talk about microns, they are usually wet etch, but not necessary as well. In some cases, when you want to etch features down to nanometer as well, you can also use wet etch. But generally, if you talk about wet etch, we talk about etching features with micron in size, 1 micron, 2 micron, even higher than that. But there are some exceptions. For example, if you want to etch, in my research, we etch silicon to form nanostructures using wet etch, HF, hydrogen peroxide, and silver nitrate in order to form black silicon, which essentially means an array of random nanowires on silicon surface where the dimension of the nanowires are somewhere 50 to 100 in terms of width. It's like nano needles. Width is about 50 to 100 nano, and the height is about 400 up to 1 micron. It can even go up to 2 micron or a couple of microns. So talking about width, so the width is somewhere on only 50 to 100 nano. So in that case, we still use wet etch in order to do the job. So usually when you compare wet etch and dry etch, wet etch is more is cheaper because you don't have to use vacuum or plasma in order to do the job. Right, wet etch is usually with high throughput because it can be done in batches. If you see, probably later on I'll upload some videos to you about wet etch, the bench. You can actually do the wet etching in batches. For example, if you talk about silicon, you can actually do silicon with a couple of batches. So that means 25 wafers per batch times a couple of batches. And the batch can also contain more than 25 wafers, and you can just soak the silicon into your bath, macam sinki besar lah, contains chemicals that you want to use for the etching, and then you can just program the process for certain time at certain temperature and with some additive if there is at all, then pick them up, and that's it, done. In comparison to dry etch, we're going to see later on, the process is going to be done in a vacuum chamber, and the vacuum chamber is not so big usually. So even though you still can do the dry etch in batches, but the size is typically limited in comparison to wet etch, where you can just put your wafers in cassette vertically and you can pack more silicon per process. So high throughput, it involves hazardous wet chemicals, hazardous liquid chemicals, just like HF, peroxide, HCl, nitric. Well, it depends on what sort of etching are you talking about. It can also involve alkaline solution like TIMA. So by the way, TIMA that used for the developer process in lithography is also one etchant option. So it's alkaline etchant, so it's tetramethyl aluminum hydroxide. You can also use that for another type of etching, which is anisotropic. You're gonna see later on. So that wet etch. So in the example that I've mentioned just now, oh, you cannot see the slide really? Okay, can you guys see the slide? Oh, okay. So yeah, I've shared already. Okay, the rest can see. Faika, can you see now? Ah, can. All right. Okay then. So this is the example of the HF etching that I've told you just now. So this one is etching silicon dioxide on your silicon. Okay, selalunya kalau you punya silicon tu, kalau you biar at room temperature, ambient condition, walaupun you dah pack dalam petri dish, usually dia akan form some native oxide on top of the silicon wafer. And that native oxide usually can be up to about 3 nano thickness. If you just leave it and you don't do anything, so you come back for your next process, you have got already 3 nanometer of oxide due to the native environment, right? So in that case, before you do your next processing, for example, if you want to deposit a thin layer of something or resist, maybe in the case that you don't want that native oxide to be there, you have to firstly etch the oxide using HF. Okay. Ada siapa-siapa kat sini pernah buat HF etching of oxide? Anyone? Ada siapa pernah buat HF etching of silicon dioxide? Tak pernah buat? Tak ada? Right? Tak ada Okay, kalau you ada native oxide tu 3 nanometer, so kalau you nak do the next process, you have to remove the oxide first. Even though kalau you tak buat next process pun, kalau you nak do some measurement, on the wafer that you've got there, you have to dip your wafer in native oxide in HF first in order to remove the oxide, or else you will probably measure the oxide part of the whole data. Okay, so this is the equation involved. So silicon dioxide, the native oxide, plus HF, so they can produce HSIF plus H2O. So the oxide concentration can be, or no, the HF concentration can be varied. Typically in the lab, we have a 49% is the maximum concentration for HF. It can even be diluted down to about 4% or 5% or even 1%. Kalau you nak remove your native oxide, usually 1% or maybe up to 5% is good enough. So what you have to do is you just have to pick your wafer, silicon wafer, then dip your silicon wafer with the native oxide into HF for maybe a couple of seconds. Bila you rendam tu, you akan nampak, kalau let's say you rendam and you soak and then you pick it up instantly, you will see that the surface is hydrophilic in nature. So dia ada hydrophilic means dia air akan lekat kat situ, akan lekat on the surface of the wafer. That means if your surface is hydrophilic or water sticking to the surface, so that means you still have your native oxide on the silicon. It's not completely removed yet. So that's hydrophilic. Kita dah belajar kan hydrophilic dekat sekolah menengah kan, and hydrophobic. So how do you tell when your HF has completely removed your native oxide? The surface will turn hydrophobic. So kalau you rendam like a couple seconds, you angkat, lekat lagi, angkat lagi, sampai satu point, maybe I don't know, a couple seconds, 30 seconds, and depends on your concentration as well. You pick it up and you see the water is no longer sticking to the surface, so that is already hydrophobic. So at that point, you can say that the HF has completely removed your native oxide from your surface, from your silicon surface. Then your silicon is ready for characterization or for your next processing. Remember? With native oxide, hydrophilic. When the oxide is gone, hydrophobic. Right, this is the example of wet etching, which produces anisotropic nature. So typically, kalau you ada silicon, for example, kat sini, let's say if you have silicon, okay, you start off with a planar silicon. Kalau you letak dalam isotropic, then what's going to happen is, kalau you nak etch structure, you're going to end up with something like that. Dia akan bulat lah, sebab dia akan makan semua direction with equal etch rates. So one example of the isotropic etching is HF. Kita tengok dekat page sebelum ni. Another case of anisotropic is called anisotropic etching. So that means for this particular etching, the etch rate is not equal in all directions, but it's higher in one direction and lower in other directions. So one example of this is by using alkaline solution such as tetramethyl ammonium hydroxide, like in developer, or sodium hydroxide, or potassium hydroxide. The common one yang orang guna, these are the three, right? Common one, timah, NOH, or KOH. So alkaline solution. Well, typically you can say that alkaline solution is generally anisotropic, acidic solution is generally isotropic. Okay, so for this particular case, if you have the very same silicon wafer just like this, for example, if you have 100, kalau you etch isotropic, you akan dapat macam ni. Kalau you etch anisotropic, you akan dapat something like this. So these unetched areas are areas yang you block. For example, you block with photoresist, you mask. You kena mask is blocked from etching process. The exposed areas yang kat tengah-tengah tu, what you will get is pyramids. Dia akan menjadi bentuk piramid. Piramid. Kalau you tak cover langsung, it's gonna be, if you don't cover at all, then you're gonna get something like this. Something like that. So you didn't cover at all. So what's happening is the etch rate in 100 orientation is the highest. Okay, so dia akan makan 100 orientation, paling laju lah, paling laju. Dan 111 orientation dia akan makan paling slow. So eventually you're gonna be left with pyramids. You're gonna be left with pyramids. Kalau you tengok 3D ya, ni 2D. Kalau tengok 3D, so it's gonna be something like this. And these planes, these faces, permukaan ni is 111. So 111 is gonna be left unetched because the etch rate is way smaller than 100. 100 is all gone. Okay, then you're gonna be end up with array of pyramids on the surface. Array of pyramids on the surface, something like this. Then you're gonna have your adjacent pyramid and adjacent pyramid. Okay, array of pyramids across the surface. So when you use wet etching, you're gonna produce surface structures. For example, pyramids. It's gonna be random in nature. Dia takkan jadi periodic because it's not replicated. It's not replicated by lithography process. Kalau you guna lithography, then you're gonna use the reticle and everything to replicate periodic structures. But for wet etching, for etching process, the moment you etch, either is isotropic or anisotropic is going to be random in nature. There's no way to produce periodic nature unless you have assistance from other process during this process. Then only it's feasible to do. Or else, it'll just be an array of random upright or inverted pyramids on the surface because that's the nature of wet etching process. Right? Okay, this is KOH or NaOH or also TMAH, sama aja. So the idea is wet etching. So atomic density of 111 is higher than 100, is higher than 100. So the most dense is 111. Right, that's why the mobility of carriers is lowest in 111, just like what we discussed before. So the etch rate of 100 orientation is about 100 times higher than 111. So that's why you end up with a pyramid with 111 face left on the silicon wafer after the etching process. It's because the etch rate of 100 is 100 times higher than 111. So that leads to anisotropic etching, and you're going to be left with some structures on your surface. All right, so next one, the typical process cycle in etching process, you normally do the etching and then we rinse with deionized water and then we dry with nitrogen, just like what you normally do in lab. So the drawback of the wet etching is mostly isotropic, but we also have anisotropic etching, just like what we discussed for the DMAH, NaOH, and KOH. Wet etching has poor resolution. So if you're talking about resolution, we're talking about small features. So because wet etch is more relevant for micron features, even though some cases it might also be good for nanoscale features, but generally the resolution of the wet etching process is poorer if you compare to dry etch. Wet etching depends on a lot of corrosive materials, which are harmful to human bodies and environments. All the acids, all the alkaline solutions are dangerous, hazardous to the environment and ourselves as well. Wet etching needs a large number of chemical reagents to wash away the residues. Yep. Well, when you run the wet chemical process in a bath, macam sinki yang besar tadi saya cakap tu, so you can run the process in batches. You can just soak all the wafers and then we wait for certain time, certain temperature, done. But to be able to make it happen, you need to provide high volume of wet etching solution in the bath in order to enable the etching process. So that in itself is quite non-economical. But generally, if you compare this to dry etching, it's still economical in comparison to dry etching process. Unless you can use lower volume of etching material to be able to do the same job than is more intended, right? You're going to save some money as well. Then you minimize contamination into the system, disposal system. Okay, wet etching, etching at nanoscale. One example, etch requirement at nanoscale. If talking about that small, for example, if you're talking about polysilicon width, the width of polysilicon of 50 nano, right? Polysilicon, you can also consider, you can call this as a gate. Usually gate is made out of polysilicon or metal, right? Well, normally now polysilicon. So if talking about that kind of etching, so what you have to have at that scale is you have to obtain the desired profile, either slope or vertical, accurately with good resolution, minimal undercut or bias. So you don't want to get undercut, just like what we discussed before. If you want to etch a structure on top, if possible, you don't want to get something like this, because this region is called undercut. Makan dalam, If possible, you want to get a straight one. Selectivity to other exposed film and resist. When you talk about etching, the selectivity has to be very high. Then only the right material can be etched for the right time, the right amount. Uniform, reproducible, minimal damage to the surface and circuits. Minimal damage to other structures as well. So you want it to be clean, economical, and safe as well, right? So if you talk about this illustration at the bottom here, so the number, the first one is isotropic, the second one is anisotropic, but anisotropy is not equal to 1, so you still have a little bit of undercut, but mostly vertical. But this one is completely anisotropic. This one is partially, if you talk about 0 to 1, it's probably 0.6 or 0.7. Okay, so wet etch done. So now let's look at dry etch. What is the difference between dry etch and wet etch? Dry etch is generally anisotropic or unidirectional. In some cases, you may also have isotropic dry etch, just like wet chemical, generally isotropic, but we do have some cases where it can also be anisotropic as well. So to be able to do the dry etch, we can do by sputtering, we can do chemical etching, we can do ion enhanced etching, we can do multiple methods, but generally it involves removal of material by etching process using plasma. So to be able to get a plasma, you need to be operating in vacuum environment. Right, any ideas kenapa kita kena dapatkan plasma dalam vacuum environment? Can we get plasma at atmospheric level? What do you think? Well, to begin with, what is plasma? Ada belajar anything on plasma before? Ada belajar apa on plasma sebelum ni? Anyone? Kita sebut plasma tu apa sebenarnya? Anyone? Fazira, what is plasma? No idea. Anyone? Who knows plasma? Plasma TV ada kat rumah? Plasma apa plasma? Tak ada idea. Go Ching Wei, any idea what is plasma? Apa plasma? Plasma tu is ionized gases. Ionized gases. Maknanya plasma tu dia asal daripada gas. Then you have to ionize the gas. Bila you dah ionize the gas tu dia akan jadi ion lah, ionize kan. Dia akan jadi ion. Ion tu je akan membentuk plasma. Okay. So for example, if you talk about argon gas, if you strip the valence electron from argon, so dia akan jadi ionization, dia akan ionize, dia akan jadi argon plasma. right? Plasma ni yang kita akan guna to do the etching process. So for etching, dry etching, we're going to learn how it's happening. Okay. So sputtering or etching, generally plasma reactors involve plasma reactors, barrel etcher, high plate, high density plasma. This is just a couple configurations of plasma reactor in order to do the plasma etching. So characteristics of dry etch or plasma etch, if you like, less selective. Okay, apa yang ada dia akan makan usually, but it depends as well. Dia banyak we call exemption. It depends on many factors as well in some cases, right? It's not like blanket for all cases. Less selective. Anisotropic etch is possible. So even though we also have some cases of isotropic white etch, dry etch, generally is anisotropic in nature. So for etching, features smaller than 3 microns. So kalau you compare to the wet etching just now, if you're talking about microns for wet etch, then normally nano size is more favorable for dry etch. Not hazardous, but well, no hazardous chemicals. Tapi ada hazardous gases. So generally they are hazardous juga. So if you talk about fat processing, I would say most of the processes are hazardous. It's just that the degree of hazard levels are different from one to another. So it contains hazardous gases like, for example, sulfur, hexa, fluoride. You can also use CH4. You can also use CF4. You can also use what else? Argon, nitrogen, many more. Depending on what you want to etch. So apa yang you nak etch will determine what sort of gas do you want to use. Sebab tak semua gas boleh etch semua material with good resolution. Okay. So for example, if you're talking about silicon, we normally use silicon sulfur hexafluoride SF6 to do the job well. Other gases won't work, as good as SF6. So plasma has RF power safety risk. If you talk about sputtering by using RF system, radio frequency plasma, you can use typically it's 13.56 megahertz for the etching process. Any one of you pernah pakai sputtering process dalam no lab? Siapa pernah sputter? Fazira sputter kan? Izian pun sputter kan? I know few more. So kita punya RF dekat kita punya sputtering dalam no lab tu, it can be either DC or RF. We're going to learn this in film deposition. DC is direct current, RF is radio frequency. So in this case, our sputtering system dalam lab tu can be used for etching as well, right? Can be used for etching as well. Cuma dia ada beberapa features yang lacking lah in comparison to standard plasma etcher, but it can be used for etching as well. You need to know the right settings in order to do the job. So in our case, it's either DC or RF. DC is normally used for metal deposition. RF is normally used for oxide, nitride, carbide, or other dielectric deposition, or even etching. Right, three types of plasma etch process. It can be either a physical sputter etch or chemical etch, or a combination of both. So what is a plasma? Plasma is an ionized gas, fourth state of matter. So kalau gasnya ialah argon, then the plasma would be made of argon plus ions. Argon plus ions. So you strip off the electrons. You strip off electrons from the argon gas, you're going to end up with argon plus, right? Significantly increases the reactivity of the gas molecules. So the moment you have ions in the chamber to do the etching, you can actually channel the motion of the ions by supplying the correct bias. So argon ion ni kan positive charge kan? So you can use negatively charged plate to attract all the ions at high speed, high energy in order to bombard the surface. Dia akan langgar. It will induce collision to the surface. right? For example, if you look at this configuration, we have a chamber here. So this one is a chamber. Chamber, you punya process lah, process chamber. So this is the vacuum pump. So kalau you pernah pakai sputtering system or maybe thermal evaporator, so we normally pump down to about 10 to the 5, around 10 to the 5 of minus 5 torr to be able to initiate the plasma. Kemudian you inject the gas, then you ionize the gas, and then the plasma will be formed here. So you can see that this one is the plasma, right? So then you can actually supply the bias to both sides of the plates in order to do the etching process. You can, for example, kalau dalam case ni, you think wafer is on the stage here and the stage is connected to negative bias. So kalau you apply a very high negative bias, for example, you bias down to 200 volt, for example. So apa akan jadi? This negative bias will actually attract the positive ions. Negative, positive, attracted. So if you can attract these ions at a very high energy, so you can actually, sebab plate belakang silicon wafer tu is all negative. So silicon is negatively charged, if you like. So you akan tarik argon ion at a very high energy to bombard the surface. If you bombard the surface at a very high energy, that is etching already. So you can remove the material by bombarding ions or plasma, in this case, to the surface to remove materials that you want to remove. So that's how the sputter etch ataupun dry etching process takes place. Right, physical sputter etch, very directional, very poor selectivity. Ions accelerated by electric field bombard the wafer surface. Ni macam saya cakap tadi, argon ions, for example. So wafer surface in this case is negatively charged due to the plate connected to the wafer. So the exact reverse process of sputter deposition here is here the wafer is the target, right? Here the wafer is the target. Kalau you sputter macam Izian and Fazira tu, you sputter silicon nitride, right? You sputter silicon nitride. So in your case, you nak sputter silicon nitride to deposit the nitride to the wafer, for example. Then in that case, your wafer dekat sini ni will be silicon nitride punya target lah. Silicon nitride punya sputter target. So you akan ambil argon ions tu, bombard on the silicon nitride material. Silicon nitride material will be removed off the silicon target, and then it will be deposited on the silicon wafer on the opposite side. So that's how the sputtering deposition works. But this one is sputtering but etching. Sputter tapi dia guna untuk etch. Kalau you nak deposit, then you can bombard the target so that the materials will be deposited on your glass ke, on your silicon, on your plastic or whatever lah you use substrate. Tapi kalau you nak etch, then your ions will actually bombard your material that you want to etch, right? So Izian and Fazira, what you did last time is actually the opposite of what I've shown on the schematic just now. So you just replace the silicon nitride on the silicon, put the silicon on the other side of the plate, and then you're gonna get your deposition done. But in that case, in this case, in our case on this slide now, is etching, it's reverse, right? So etching and deposition is just the opposite process. It's just how you manipulate the connection of your electrodes and how much voltage you need to apply in order to initiate the job. So in this case, ions are removing the exposed area, right? Ions are removing the exposed area, so the areas will be etched. Originally, perhaps semua ni akan jadi black, originally. Sekarang dia dah remove itu. Originally, maybe all these are all black. Assuming the black one is silicon, right? So yeah, then you're gonna remove. You're gonna drill the drain or trench. Kadang-kadang kita panggil ini sebagai trench. Lubang tu, trench. TERNCH. Right. Alright, so next, chemical etch, a non-directional, isotropic, high selectivity. In this case, free radicals used to be able to do the etching process. Plasma creates highly reactive species called free radicals instead of ions. So bila you nampak free radicals, it's chemical etching. Radicals are not charged, so there is no directionality. So kalau kita compare dengan yang tadi, argon ions are charged, positively charged. So you can actually manipulate the negative bias behind your silicon to be able to direct the ions, but in this case radicals are not charged, so they will travel quite everywhere, literally everywhere, and etch all directions with a similar etch rates. So useful for blanket film removal, for example, etching of resist with oxygen. Ada satu lagi proses etching yang kita panggil ialah etching. Etching. Dia bukan etching, but etching. So remember last time when we talk about lithography punya rework process kan? Kan saya cakap kalau tak jadi proses, you have pattern collapse or whatever, then you need to strip off your resist in a rework process and then repeat the CAD all over again. So stripping the resist in that case is done by etching process. Etching. So you etch the resist with oxygen plasma. Kita pakai oxygen plasma. And then you send your wafer after CAD, sebab your CAD tak okay ke, overlay is out or whatever, you just send the pattern resist masuk dalam etcher bukan etcher, then you inject oxygen plasma, then it's going to etch the whole resist surface, then you're going to end up with a very clean surface, just like before the CAD process. Then you send those wafers back into CAD process to repeat lithography. So in that case, it's called etching, and it's done by free radical, right? So argon ions are unidirectional untuk unidirectional etching or sputter etch. For chemical etch, we call it etching. We use radical to do the job. There is also another process which combines both physical and chemical etch. So which combines ions and radicals to do the etching process and the etching process, if you like, combined. So combines directionality with good selectivity. Sebab satu tadi dia good directionality but lack selectivity. The other one lack directionality but good selectivity. If you combine both, you're gonna be 2 plus 1. 1 plus 1 equals to 2, and that one is more powerful than one alone. Each one alone. So used for patterning of submicron features through photoresist. Well, this one is not blanket as well. It depends on what sort of structures are you talking about. If the combination is okay to produce the features or the profile that you want, so you can just go ahead and use the combination of the radicals and the ions to do the job. If it's not okay, then you might want to just go for ions to do the job, right? So whatever it is, you have to test and see whether your DICD, FICD, DIFICD bias and everything else in process specifications in order to do the job. Let me go through another, maybe one or 2 pages. Dry etch, okay, maybe just this page, I think. Maybe just 2 pages, right? One of the examples of dry etching is called RIE. Kita ada dalam non-lab, tapi sistem ni tengah down. Maybe akan up early next year. Dah dapat budget untuk repair. It's called reactive ion etching. Reactive ion. E tu for etching lah. Reactive ion etch. It's a highly selective plasma etch process. Right, kalau you nak etch structure yang very small, very thin, or hole very thin, or small hole, RIE is your choice, right? So highly selective, highly anisotropic, this process, right? So you can have a look at your polysilicon, a very thin polysilicon in this picture, then a very thin layer of gate ox, 3 nanometer under the polysilicon, and it's very periodic in nature, very periodic, right? So nampak tegak tapi is macam memanjang. So in that case, we need to use RIE to do the job. 26 nanometer of polysilicon gate. So the width of the polysilicon in this case is 26 nano. So etch stop on 3 nanometer of silicon dioxide for the gate ox, and you have this structure. Another one is called, it's not only RIE, but it's also combined with DRIE. DRIE is even better than this. It's also used for silicon etching. This one is by Bosch. So you can actually engrave, macam engrave structure lah, tulis-tulis nama or whatever. You can use the DRIE process, especially if you're talking about a very deep structure. Kalau macam tadi, tengok kat page sebelum ni, it's just like, what the height is like, what, the scale bar is 200, perhaps 200 plus nano, the height. So it's not that deep. So in comparison to this structure, kalau you tengok Bosch punya height tu is about what? The scale bar is 90 micron. So this is possibly 110, 120 micron depth. So you need a very deep plasma anisotropic, deep anisotropic plasma to do the etching. So in this case, DRIE is used, deep RIE, if you want to go for deep etching process. So etching ni pakai SF6, right? SF6, and you can see the illustration there, but it's deep in nature. Right, okay, I'll just stop here. It's 2:50. So we're gonna continue with the rest of the etching tomorrow. We're gonna finish with etching. And then I want you to have a look at this case study on page 44. Okay, page 44 ni on the lithography capability in combination with etching. Sebab soalan ni kadang-kadang soalan is not only on lithography, it can also be a combination of litho and etch as well. I want you to have a look at this, think about this, and think about the solution as well. And we're going to discuss tomorrow on what is your proposal for this process. Just like the way you proposed for your CD in the test yesterday. Okay then, any questions for etching? Can you follow so far an etching process? Okay. All right, we're gonna continue tomorrow. We don't know yet the status for your coming back to USM after the big sem break, right? It's just 2 weeks away. It's supposed to be 7th of December. But I'm not sure whether you're gonna be allowed to come back or not. Sebab untuk kita punya course ni actually there is a mini project that you have to do in the fab, in the lab, not in the fab. In the lab, you have to do that in groups. But if you're not allowed to come back, then I'll have to rearrange the plan for your presentation, because your presentation that accounts for the final 30% will actually consist of the lab work plus the presentation itself. So that's why it's worth 30% for one presentation. But if the lab work cannot be done, then I'll do some rearrangement of the project so that you can present eventually for your presentation mark. But let's see, it's just 2 weeks away and the numbers are not encouraging now. It's over 1,000. Semalam 900 plus kan, 970, and day before was like 2,000 plus. And Klang Valley is hot now. Selangor lagi tinggi daripada Sabah kan, number of cases. So well, let's see. I'll need to plan on that. And in the meantime, just stay safe. If no questions, I'll see you again tomorrow, inshallah. Take care. Bye-bye. Assalamualaikum.